Support for Knowledge Stream comes in part from a generous contribution provided by an anonymous donor.
It's a non-trivial task today because they know the diameter, but they don't know the optimal algorithm from every position. They just could prove that it's less than that or equal to it. Okay, so here's a picture of me this week in Ann Arbor at the G.G. Brown building. They have the world's largest stationary hand-solvable Rubik's Cube. It weighs about 1,500 pounds. It was a student project. Their engineering students made it, and it's really interesting because you can't just copy the internal mechanism to be that large because there's too much friction. The friction's what holds it together on the small level, but up here you wouldn't be able to turn it by hand if you didn't do something different with the internals. And it weighs 1,500 pounds. I was lucky enough to get a chance to solve it. I failed. But anyway, that's something you have to learn to deal with if you want to solve puzzles, is you're not going to be able to solve all of them. So some quick facts about the Rubik's Cube. There are about 4.3 times 10 to the 19th configurations of the cube. So I did a little computation. If you could turn 99 turns per second, and each time you did one of them, you got to a new position, roughly you could get through every position if you did that from the beginning of the universe till now. So sometimes you see some hoax things where people say, I found an algorithm, it will take you to every solution. No, if you could do that, you'd have to be able to go through half of that, so 4.6-ish, 6.5 times 10 to the 19th positions on average. So those sort of algorithms don't exist either. Okay, so I want to show you guys a quick video of the world record solve for a Rubik's Cube. Now, I want you to pay attention here because they initially get, like, I think it's 15 or 30 seconds, I think it's 30 seconds inspection time before they solve the cube. So what they're going to do is he's going to look at it, he's going to set it down on the mat, put his hands down, which they're timed by the hands, and then he's going to pick it up and solve it. So let's take a look at that. I've shut off the sound. So he's inspecting, hands down. That's the world record single solve. You see 4.519. And they just keep getting faster, but that's the nature of a world record, right? Now, I want you guys to notice something else here. How old are these people? Yeah?
He should be about 21.
21? I thought he solved it last year.
Well, maybe 22.
Maybe 22. Okay, but I mean the other people around here solving too. These are fairly young people. You can get to the very top level of speed solving around 15. That's not uncommon. So this is something that I think is good for all of us to realize. This is, if you follow an appropriate strategy, anyone can learn to solve the Rubik's Cube. It's going to take some effort. It's going to take a little bit of memorization, and you're going to have to find a strategy that works for you. But anybody can do this. Now, not anybody can do it at 4.5 seconds. That's exceptional. And he probably got a little bit lucky. He might have skipped some steps in there. And occasionally that happens. So anyway, that's the current world record. Let's see. Okay, so some faux pas. If you meet someone with a cube, if they let you handle it carefully. Don't go, with it. They really don't like that. People who are speed solvers, they take a lot of pride in their cubes. They set them up meticulously. They adjust the tension. They buy special purpose lubricant that won't melt the plastic, which basically comes in like little syringes because the propellant in the lubricants you'd buy in the stores will melt your cubes. The other thing that everybody says is, I peel off the stickers, or I peeled off the stickers. And let me give you some advice. If you're going to cheat at the Rubik's Cube, cheat well. The best way to cheat, and it's kind of instructive, is to take it apart. So I'm going to take apart a Rubik's Cube here. And let's switch to the document camera so you guys can see kind of what this has. Because there are some important observations that we can make about a Rubik's Cube by understanding its internal mechanism. So here's the first piece I popped off. Then I have, this piece is actually, I think, a little broken. But, let's zoom out. Now, I don't necessarily recommend actually taking it apart, because it's possible you could break it, but, and it takes a lot longer to put it back together than it does to actually solve it, even if you're pretty slow like I am. Okay, so first observation I want you guys to make is if you look at this internal mechanism, the faces are fixed. So they are always going to be in the same orientation to each other. So if you're coming up with a solution strategy, you can basically ignore the faces. The other observation is there are different types of pieces. We have pieces with 2 stickers. I call those edges. You have pieces with 3 stickers. Let's find one here. I call those corners, and I think everybody calls those edges and corners. And no matter what you do, these are always going to have the same relative position of these colors on them. They're not going to change when you move them around. So the higher level way of thinking about Rubik's Cubes is actually to think about blocks and the orientation of the blocks rather than thinking about the stickers. So let's switch back to the computer here. So I've said a lot of this. So the cube comes in blocks in which stickers keep the same relative position. There are 3 types of blocks. There are faces, edges, and corners, and all the faces are fixed, so you don't even really need slice turns like the ones I told you guys to do at the very beginning of my talk. You can just do side turns if you like. So before YouTube, people were still using the internet to try to talk about solving Rubik's Cubes, so they needed a notation. And there was a mathematician named Singmaster, I think I spelled his name right, who came up with what's called Singmaster notation. So the idea is you fix the orientation of your cube, and then you think about the different faces. There are 6 faces, so think up, down, right, left, front, back, okay? And then they use those letters to represent those particular moves. And if you go clockwise, they think of that as the forward direction, and they put a prime. I like thinking of that as an inverse, but prime is a lot easier to write, and that's what they write, or a little single quote on it. That's what I mean by prime. To mean going the other direction, counterclockwise. And they put a 2 next to it if they mean turn it twice. So this is an early way people would communicate solution strategies to Rubik's Cubes, is they would, and I think if, these didn't come in boxes. When they come in boxes, oftentimes there's a little thing that explains this notation and gives you some algorithms for solving it. And I keep using this word, but I haven't really told you what it is. So if you're a beginner, a reasonable strategy for solving a Rubik's Cube is to build a solved cube a layer at a time. So the first thing you want to do is you want to solve a cross. And I'm going to push my taken apart cube off here. Hopefully I find all the pieces. So basically a cross. I call this one my cross trainer. I've taken off all the stickers except for the center faces and the edge faces and the cross. Now, you can solve a cross for whatever face you like. I was practicing with when I made that cross trainer, and usually, because that's the one that I learned to solve first. And you basically want to keep solving the first cross the same way until you learn how to solve the cube as a whole, because it just gets a little bit more confusing, because what you want to do is kind of like what I did with this puzzle. You want to ignore all of the other stickers except for, let's see, these 5, 1, 2, 3, 4, 5, 6, okay, these 8, and this 1. So you basically want to ignore everything else. And sometimes it's helpful for some new beginners, I let them use this because it helps you ignore them, because it gets rid of all the other distractions. The next thing people do is they usually solve the first 2 layers. Some websites recommend that you solve the bottom layer, then you solve the middle layer. You actually need a lot more algorithms to do it that way than to do the first 2 layers. And then you solve the last layer. So again, I just described the cross a little bit. Here's a picture of what a solved cross should look like, and I grayed out all the other stickers, and that one's just like folding out the bottom and the sides so you can see all sides of the same cube. Okay, let me talk about solving a cross. Most people say it's a good idea to just learn to solve a cross intuitively. There are less than 8,000 possible positions, and just by moving things around, you can get a pretty good idea. It helps to have strategies like if you break something, do something, put it back. That sort of strategy is really, really helpful. So if you can move something out of position, do something useful, then put the thing you moved out of position back, is a useful strategy in this phase. Okay, so after you learn how to solve a cross, the next thing you want to be able to do is solve the first 2 layers. And a reasonable way to do that is to put pairs of edges and corners together. So if you have a solved cube in front of you, and what they call an F2L pair would be a pair next to the cross of a corner and an edge that match, and they're put together in the correct orientation. So down here I have just a pictorial representation. So this one, the cross is already solved, and I move the top piece around, and then I connect the F2L pair, and then you put it into position in what I think people call the slot next to the cross where things go on the F2L pair. So people also suggest that this is intuitive to learn. I did not have much luck until I found, you can look it up on YouTube, Hunting F2L. It's probably one of the nerdiest videos you can find. He uses animal metaphors to do it. Rito, I think, is the person. And once you found the really corny music, you know you're at the right place. It is so good, though. It helped me learn this, and this is a useful strategy.
Hey,
yeah?
Can you just walk through the steps of getting from each of those to the next one?
Sure. So on the first one, I did an upper level twist to get to the second one. And then I did a front twist to connect the F2L pair. And then I did another, this one's the upper level twist in reverse. And then I did a front twist to put things in position. So I'm connecting things using essentially 2 moves. I'm using upper, front, upper, front. But I mean, they're not all in the same direction. Now, something you guys should probably know about me, the letters way of solving things is not very intuitive to me. Yes, yes?
Don't you only want to solve F2L pairs in the back?
Yeah, you need to solve 4 F2L pairs, and there are some in the back, and
Yeah, but it's
some.
more efficient because you've got more to look ahead.
Okay, yeah, I think you're probably more advanced than I am at it. I'm just a babe in the woods. I just look this old. So yeah, so you're right. There are more efficient ways to necessarily do this. There are 4 of them that you have to do. Myself, I usually just rotate the cube, keeping the same vertical axis, and until I put them in front where I can see them. But you're right. If you can do it in the back too, that will be more efficient. It's just a matter of developing the right sort of techniques. Okay, so after you've solved the first two layers, you can solve the last layer. And there are a couple of different strategies for the last layer that I've seen. The main one, so your cube should look something like this once you've solved the first two layers. So the bottom two are fixed and the top is all scrambled up. So to do this layer, you're really going to have to use an algorithm. And this is the word that we kept using, but we haven't really defined a set of rules that precisely defines a sequence of operations. Now, a lot of people list algorithms by just listing these Singmaster notation letters, like they might say R prime, L, R, L prime. That would be an algorithm. But myself, I do algorithms, but what you guys should probably know about me is I probably have a reading disability. My brother is diagnosed dyslexia. They were concerned about it with me. And if you ask anybody, I read words sometimes and they say, that doesn't say that. Then I look back at it and the letters have moved around. So you can understand that looking at long lists of letters is not a good way for me to learn how to solve a Rubik's Cube. I use sort of spatial intuitions and basic sorts of algorithms to do it. It doesn't make me any better or worse. It probably makes me a lot slower than most people at it, but you know, you can learn to do this even if you have a disability. If you're colorblind, they have sticker packs that you can put on a cube that you will be able to see the different colors. If you're blind, they have Braille stickers that you can put on a cube. So anybody can do this, you just have to get the right sort of thing. So the main strategy that speed solvers use is they do the last layer in two steps. They orient the last layer, so as you can see in that picture, that's what happens after you orient the last layer, is you've made it so that the face is the right direction on all of those blocks on the last layer. And then they permute those pieces, meaning just move them around so that they're in the correct place, and then they're done and it's solved. So some people call this Friedrich, after an engineering professor who posted really extensive instructions and videos on how to do this online on her personal web page, but a lot of people call it CFOP, cross F2L, orient the last layer, permute the last layer. And I'm pretty sure this is the dominant strategy for speed solving. And the reason why it tends to set world records is if you're clever with your F2L step, you can omit or get into a really easy case of the orient the last layer. And I think people call that edge control. I have no edge control. But if you get lucky, those last two steps, you can get a total skip. The other day I was solving and I oriented the last layer and it was permuted. I got a PLL skip. That's pretty unusual. Okay, so advice to learning, you can do it. Make sure you fix an orientation. Always start solving with the same cross, the same side of the cube, because even Felix Zemedges, who holds multiple world records, he says he's not, oh gosh, I'm blanking on the term, color independent, I think they say. Color neutral, yeah, that's the term. He says he's not color neutral. He just does either starting with the green or the blue face. There are people who are color neutral that practice solving the cube on every orientation, but that's something you don't want to do when you're first learning. You want to pick one face to be your beginning face and go with that. Don't worry about accidentally mixing it up. Is that, okay, I'm not a scientist. Isn't it the second law of thermodynamics that a system tends towards entropy? So it's going to tend to be in any random state if you just play with it randomly. So don't worry about it. It should be mixed up. You're going to get some good practice in the first few steps every time. So don't worry about being perfect. Google and YouTube are a big help. I think YouTube has made it a lot easier to learn because now you don't necessarily need to figure out what all these strings of letters mean. You can look and see someone doing it on a video, which is a big help. I don't know of a Toledo local club, but But there are World Cubing Organization events in Ohio. There's one today. Okay, so I want to talk to you guys a little bit about how this is useful as an abstract concept. So you can think of every permutation, which an algorithm on the cube, we can call them permutations, as an operation. And these operations have, you know, some properties that you probably were told in like an algebra class or a math class, but you maybe just used without having to think about them very much. The first one is the associative property. That says you can put the parentheses of putting any two of them together anywhere you like. So you can group them by two however you like. And that's what allows you, like when you're multiplying numbers, if you want to say 5 times 7 times 8 times 12 times -1, you can just write them out. You don't have to put parentheses around every two of them. And so these permutations have that. So that means they can make these big lists of letters that mean moves as much as they like. There's an identity. We can all perform this one. I perform the identity operation. Done. You don't do anything. That's the identity. And every operation has an inverse. Now, this one you can definitely see if you just do a single turn. So if you turn one side, what's the inverse of that? Yeah. Yeah, you turn it back, the opposite direction. Now, it's not entirely clear. Well, I'll tell you guys how you can do it with other ones. Okay, so any object that has these properties is called a group. There are whole areas of mathematics, people that specialize their entire life on groups. I'm one of those people, actually. So here's one property that is a big property that you're used to in numbers that doesn't happen on groups or Rubik's Cubes in general. It's not commutative. So the order that you do the operations, it matters. So if you do a right-hand turn, and then you do an up prime turn, that's going to be different if you do an up prime turn than a right-hand turn. That's what I'm demonstrating here. And all you need to do is look at those last two positions and see they're not the same. And that shows you that this is not commutative. So that's a big property that we're used to in numbers that a Rubik's Cube doesn't have, and groups in general don't have. Now, those two-turn thing that I showed you at the beginning, that's what's called a commutative subgroup, because it's also a group if you only do those operations, but it's commutative. Okay, so I want to teach you guys how you can invert any arbitrary string of operations. And all you have to remember is socks and shoes. So how do you invert the operation of putting on your socks and putting on your shoes? Yeah.
Socks?
Yeah, you take off your shoes, you take off your socks. And this actually holds in the mathematical sense too. If you're taking the inverse of a composite operation, you socks and shoes it. You do the inverse of each part in the opposite order. So what this means is if you can keep track of every operation done on a Rubik's Cube, list out the operations, reverse the order and invert each one, you will have taken it back to the state that it started in. So there's my very simple mathematical formula for socks and shoes. You can make it as long as you like because we have the associative property. So some more concepts from group theory. Remember that strategy? I said, do something useful, or move something out of the way, do something useful, move it back. That operation is called conjugation in mathematics. And what it does is it preserves the shape of the operation y, or it preserves the sort of structure of the operation y, but it moves around the result of it by the structure of x. Another pretty useful operation is what's called a commutator. Now, if the operations were commutative, you could move the x prime towards the x And this would be the identity, because they just multiply together to give you the identity operation. But since they're not, they can give you some useful things. So I want to show you guys just some quick examples of commutators, because this was originally the way that I would always solve a Rubik's Cube. So here is a 3-cycle commutator. If you're a cuber, this is kind of soon. S-U-N-E. So this is a commutator, and you can see I conjugated one of them. And the idea is if you can come up with 2 operations that only move one thing in common, the result will be a 3-cycle. What do I mean by a 3-cycle? Well, if you look at this one came from here, and then this one came from here, and this one came from here. So there are just 3 things moved, and they cycle with each other. That's what we call a 3-cycle. Let's play it again. So it does the first operation, does the second operation, then it goes in reverse in the inverse of each one. So that's a 3-cycle by a commutator. Now you can do the same thing with edges. I've kind of cheated and used slicing moves in it also, but that's the way I knew how to do it when I did this one. So this is a 3-cycle, you can see, with these 3 edges on the front face. And you can do a little bit more complicated ones too. This is an orientation preserving 3-cycle, and you can see those letters on the first-hand part of my commutator. That's a lot of letters. And I don't remember this by letters. The way I remember this is I think about the path of the piece from the top layer. So I think I switch 2 pieces from the top layer, then I turn the top twist, the upper level twist, the U, and then I switch the 2 pieces from the top layer back, and the result gives you an orientation preserving 3-cycle. So commutators is a structure that the nice thing about them is it makes it so it's simpler to remember an algorithm that's kind of long. Because you see, if I think this is a commutator of x and y, that gives me 4 times as much stuff to do as just x or y together. So, well, maybe twice as much stuff to do. So it's giving me a little bit of saving in my memory. And if you can make these things and think about them in terms of moving one thing to another place, that can turn it into spatial memory instead of memorizing a list of letters, which I'm really, really terrible at. Okay, so I'm just about finished here. So another sort of deeper thing from group theory is that since the Rubik's Cube only has finitely many states, if you repeat an algorithm enough times, it will undo itself. The one that I think speed cubers use is, this is kind of a weird cube. It's only got 3 colors instead of 6. But if you repeat an algorithm enough times, I'm just doing the same thing over and over again, it undoes itself. That one has order 6. You do it 6 times and it undoes itself. This is called Lagrange's theorem in group theory, or at least it's a way of stating Lagrange's theorem. Okay, so what about impossibility problems? There are a couple of types of impossibility problems. The 15 puzzle we already saw when we interchange 2 pieces, you can't solve it. The Rubik's Cube has its own impossibility problems. If you change the orientation of one corner, you can't solve it. If you change the orientation of one edge, which is kind of tricky to do, you can't solve it. If you switch either a single pair of corners or a single pair of edges without switching anything else, you can't solve it. So this is actually related to this mathematical concept called parity. Yeah?
I was going to tell you what parity is.
Oh, okay. What's parity?
It's where 2 edges, or it only occurs on full left or up, but when an edge is flipped and it's an annoying algorithm that you have to memorize.
Yeah, it is an annoying algorithm, especially on like the 4x4x4 cube, or 6x6x6. But it doesn't usually happen too badly on the Rubik's Cube unless you break it. So parity mathematically, the easiest example of parity is even and odd. If you have an even number and an odd number, and you add them up, what kind of number do you have? So 3 and 4. It's an odd number. And it turns out no matter what even and odd number you add up, you're going to get an odd number. And the same thing happens. If you add 2 evens, what do you get? Even every time. And it turns out that you can get a subgroup of what are called even permutations. Essentially what you do is you count the number of transpositions you can build a permutation from. And there can be a different number, but they're always either even or odd. Transpositions means you just switch 2 things. And so sometimes if you end up with an odd permutation, a puzzle won't be solvable. Okay, so I wanted to take a moment to talk to you guys about different types of puzzles. Probably my favorite, most recent thing to do is to solve different colorations of puzzles. I did a student project with Alex Aldana last year, and we analyzed, he derived every possible coloration scheme, and he derived the order of every group. And the interesting thing is when you have a cube like this, like you see I have edges that are monochromatic, they're one color. That actually makes the puzzle harder. Also, I have identical edges, 2 edges with exactly the same coloration, like I have a yellow and orange there, and I have another yellow and orange here. Those can be interchanged, and you can't even tell. So that gives you parity problems. Some other sorts of puzzles that you can have higher cubes, like I have a 5x5x5 Rubik's Cube here. You can have, I don't know where my 4x4x4 is. It's probably in one of these bags. You can have 4x4x4 cubes, and some of these higher cubes have identical edges too, so you can get parity problems in those as well. You also have things that are called shape mods or shape modifications. Here's an example of a shape mod that someone found in the dollar store and gave me yesterday. Basically, it's just an internal mechanism that's identical to a Rubik's Cube, but it may have like a different shape, you know? So let's see if I can do, here's the cross in this puzzle. You know, it looks a little different. This one, the shape doesn't change too radically. I have this mirror block. These are kind of fun puzzles. They are a shape mod of our 3x3 Rubik's Cube. And their cross looks pretty fun, right? That's a cross. It's got stuff going each direction. And the way you can tell where each piece goes is by the shape of the piece. Now I have a ghost cube, which I made it about to the first layer, and then I went, okay, I can figure out how to solve this, but man, I have no idea how to tell which piece goes where without just doing trial and error. So every puzzle will drive you nuts in its own special way. And you know, I have a collection of puzzles that I don't know how to solve also. The Scube, which is supposed to be easier than a Rubik's Cube. It's got like these deep slicing cuts. No idea how to solve. Here's a restickering of a Rubik's Cube. I've been too chicken to even take out of its box. A Sudoku cube. It's got the numbers 1 through 9 on each one. From what I understand, the way you tell where pieces go is by their orientation, which, how do you know the orientation of the numbers on the outside and what they're supposed to be? I'll have to study this really hard before I think about it. There are other sorts of shapes cubes, like this isn't really a cube. People still call it cubing. Icosahedral thing, people call this the Megaminx. This one is not really that much more difficult to solve than a Rubik's Cube. It's fun though. Instead of 4 first 2 layer pairs, this has 20. So good practice there. There are these cuboid sort of puzzles. This one, it's a 3x3x2. I thought, oh yeah, I'll be able to solve that. I got it out and mixed it up and realized I didn't know how to solve it. It took me like a month to figure out. There are some puzzles where there isn't really a solution. They just make different shapes. This is like, I think they called it a Rubik's snake. You know, you can take it apart from this cubey shape to something that's like a straight line or different shapes. This one's fun because you can invert the color pattern. That's maybe one way to solve it. And yeah, I think though, you know, directed at maybe parents here or people who are questioning the value of this, there are really some good things that you can learn by looking at puzzles like this. You learn good dexterity skills. They're pretty much doable by anybody who's determined enough. They teach you some concepts that are useful in higher mathematics and chemistry and physics, and they're fun. So that's all I have for you guys today. Oh, I didn't show you guys a square one. Oh, there's my 4x4x4. So there are some types of puzzles that are more like the 15 puzzle. I like thinking of them as groupoid puzzles because the mathematical object that they make is a groupoid. And a groupoid is just like a group, except the state that you're in restricts the operations that you can perform in it. So a Rubik's Cube, you can always do any of the operations. The square one cube, well, it's not a cube anymore. It depends what shape you're in, what operations you can do, because you can't always slice all the way through. And the 15 puzzle has that property too. Depending on where the hole is, you can only slide certain things. So I don't know how to solve the square one either. I'm just happy to be able to get it back to the square shape at this point. Anyway, does anybody have any questions? Yeah.
With the 15 puzzle,
Yeah.
I accidentally get it in it. What does it mean when you say you can't solve it? If you accidentally get it like that, you just stop it.
Well, I think what people did, the 15 puzzle, what happens if it gets in that position? I mean, I'm going to try to go back to my 15 puzzle picture. So what I think Sam Lloyd did is he took out ads in the paper, and he's like, buy my puzzles. If you can demonstrate how you get from the starting position to this position through legal moves, I will give you $1,000. So they were like little dovetail joints that fit together and it would slide around. And so obviously, I'm pretty sure he knew you couldn't do that. But when you have a physical puzzle, you could just like pop it out and put it in that position to torture someone. Just like with a Rubik's Cube, if you want to make it impossible to solve, ooh, trade secret here, everybody, you can just twist a corner. But, you know, it is actually legal because sometimes, like, a solver during competition will end up with a twisted corner because there's corner cutting. Like, you can twist these a little bit even if they're not there, and sometimes that will twist a corner. They're allowed to adjust any unsolvable positions. Now, for a 3x3x3, since to get a world record, you have to be under 10 seconds. That's not efficient. But for like the 13x13, I've seen videos of people where they're puzzled, they turned it and it broke apart and they're like, oh, and they get the pieces and they start putting it back together because they can still win the competition because it takes that much time to solve the bigger puzzles. So, but it doesn't usually happen for a 3x3x3. I think there's some famous videos of some really good speed solvers almost having a world record, but they had a corner that twisted in their solving process. So that can happen. So if you have just one corner twisted, you can kind of twist it yourself. I don't necessarily recommend that. If you're not too careful, it can break your cubes. Yeah.
With cubes like the square one, where the kind of how the cube is able to turn based on individual pieces, is there still like a solid method for solving it, like with the Rubik's Cube, or is it kind of intuitive based on the physics?
I haven't really done too much research because I like to try to figure these out myself before doing it. But I think there are solution strategies. But I think the first step is understanding the shape space. If you think of these as functions, it's basically like you're taking the domain and range of the functions and you're just restricting them. So these ones can only go between this domain and range. These ones can only go between these ones. So it's like stringing together functions. So the square one there is definitely a solution strategy. There are speed competitions for this. I really see what happens in this is there's only a 180-degree turn that you can do. They always show pictures of it like this, but that's not really a legal position. So you flip it 180 degrees, and then there are some places that there's an all the way through cut, maybe some that there isn't, like here. But you can see that there are cuts. So that's how this one restricts it. If I really was motivated, I could get online and find some guides on how to solve it. But I'm enjoying just having these perpetually mixed up puzzles at my house that I can play with and try to solve every now and then. I've invented my own notation for the square one. It hasn't helped me yet. Any other questions?
Okay, if there's no other questions, let's thank Dr. Iverson.
Support for Knowledge Stream comes in part from a generous contribution provided by an anonymous donor.